Hello, I'm Yegor Prikazuk, and this is the user guide of SCOPE, Soil Canopy Observation of Photochemistry and Energy Fluxes model. Today, we are going to speak about a time series run. So it's set option simulation equals 1. We are finally going to touch weather-driven output, such as fluxes. So we are finally going to talk about this part of the scheme and not only radiative transfer. The important concerns here are interplay with soil heat flux, G or SHF, that we are going to cover with soil heat methods. So those options have to be aligned. And there are many other questions that we are going to touch upon. What I expect you have already done is you went to our GitHub and you downloaded the model with download zip. After that, you have unzipped the file, and now you can navigate to Scope Master, and you see these files. Also, of course, you have MATLAB, which would normally start with double click of Scope. See that the Scope is open, and we run it for the first time. The first run has 100 simulations, and hopefully you get the same message that the output is the same as in the verification dataset, which means we are good to go. What I also expect you to do is to find our documentation. The link is directly in the README. Here in the Scope documentation, we are going to talk today about model capabilities of energy balance in the first place. So here you can find short explanation on what it is, and time series runs. So how to see, in this case, diurnal cycle or annual cycle, how to run Scope in this mode. Time series mode is arguably the most often used mode for research. So the options that we are going to cover are rules of input reading, and this is simulation option 1, time series, and also variation in input, which is how to compute a soil profile. But this a bit later. Let's go to our main folder, and as always, we go to input. We are going to change the 3 files, file names, input data default, set options. Starting with set options, we are going to say that we do not want verify anymore, of course, line 80, and the simulation is 1. It's a time series mode, line 11, 1. We save it, and this time we're not going to close it because we will need to adjust this option some time. Then input data default, we don't have to change anything here. And then we open file names. File names is the key input provider for time series mode. So in these 2 column file, probably you already know, in line 4, we just change the name. We give name to our simulation. I will call it time series 0, and I save it. And now we can take a look at what are the other parameters about. So line 15, dataset dir, says the dataset dir is for verification. And inside that folder, we have the CSV file with meteor data, which is called input data latent hypercube ts.csv. Let's see. It's an input. We have dataset space for verification. We open this file. We open this folder, and we see this file. Let's take a look what is inside. So inside, we see some parameters. We see 30 rows of values, T, then something that looks like chlorophyll, leaf chlorophyll content, leaf carotenoid content, VC max, incoming radiation, and even geometry, soil zenith angle, observation zenith angle, relative azimuth angle. All right, let's see how it reflects in file names. So we go down, and what we find, the line 34, variables below are column names in time series files. Okay, so these in column B, these are column names in this file. Yes, we see they exactly match. All right. Let's save it. Let's again keep it open. This one we can close. And we can go backwards and one step more backwards because we have to adjust, as always, set parameter file names file. Specifying that our set options file is correct, file names is correct, but input data, we don't want Leti Hypercube. We want default. Save it, close it, go to scope, run it. What we are expecting now, we are expecting 30 simulations because the file that we have just seen has 30 rows. Indeed, there are 30 simulations. We see that in contrast to previous runs, in time series simulations, we have time, so it attributed it to the January 2020. By default, 2020 is a year. By default, column T is treated as day of year. And that's what the first warning says, that I don't know what exactly time it was. So I'll try to guess it, that it's a day of year, and the year to which this day belongs to is 2020. That's why we see the numbers from 1 to 30 were converted to days from 1 to 30 of January. There is another warning that we computed actual humidity, EA, from air temperature and relative humidity. So these are only warnings. We don't have to be worried about them. And I just explain you what they mean. They just warn you about something. As well as this one. There is also a warning that speaks about energy balance closure. When you see the numbers are like this, you also may not worry about that. But later we'll discuss what it is. So let's take a look at the output. And in order to look at the output, we go to output folder. We see our time series 0, and we open our file fluxes. To understand what those columns mean, we need some background on energy balance that I'm going to provide you now. So energy that comes to Earth as the energy from sun, is radiation from sun, is reflected, but the rest, the remainder that is incoming minus outgoing, is called net radiation. It stays on the surface. The energy cannot stay on the surface. It changes its form to two convective fluxes, latent heat flux, lambda E, and sensible heat flux, H. This one evaporates water, this one warms up the air, and the conductive flux, G, that one warms up the ground slowly. This is what happens during daytime. During nighttime, there's no sun, nothing, no radiation comes to the Earth, maybe from clouds a bit. That's why net radiation is usually negative, and the surface loses its energy on evaporating something still, because latent heat flux is positive quantity, and the surface gets energy from soil. Lower layers of soil warm up the surface, and the air above it warms up the surface. So sensible heat flux and ground heat flux at night are usually negative. So those are abbreviations, and going back to fluxes file, this is net radiation of canopy, C, so of vegetation. This is net radiation of soil, and this is total net radiation, canopy plus soil. Scope is a two-source model, so we separate canopy and we separate soil. LEC is latent heat flux of canopy, which is transpiration, if we convert units to millimeters. LES is latent heat flux of soil, evaporation, and this is their sum, evapotranspiration. This is sensible heat flux of canopy, this is sensible heat flux of soil, this is their sum. And G tot is, of course, only exclusively soil flux, so there's no S or C. This is what it is, soil heat flux. So this output corresponds to variables we saw. Now I have to admit that even if we plot it, the graph doesn't look so lovely because those variables were not actually the true daily meteorological data, but it was rather a latent hypercube sampling. If you saw one of the previous videos about lookup table sampling, this is an example of a more smart way of sampling lookup table. That's why we cannot really discuss here many things. That's why I suggest closing this file and adjusting our input properly to account for the true meteorological data. But one thing we have to remember when we do this is this. When our input data has sub-daily steps which are shorter than 3 hours, so let's say we provide meteo data every minute or 15 minutes, half hour, every hour, the ground heat flux is not zero. We cannot assume that it's zero. We have to compute it somehow. It's a positive number because during daytime, soil is getting warmer. And that is what we do with options soil heat method 0 or 1 or 2. The simplest one is 2, when we just take 35% of soil net radiation. The more advanced options are options 0 and 1, where we compute soil inertia from constants or from soil moisture. And then this is the only moment when scope acts as a thing with memory. So scope remembers 12 previous timestamps, soil temperature of 12 previous timestamps, and with option 0 and 1, it uses it and soil inertia to compute the actual ground heat flux. So this is for sub-daily data sets. These options are, by the way, also explained here. Variations in input, soil heat method 0, 1, 2. What is not yet described, but is already implemented in scope, that if we work with daily average data, we're safe to assume that ground heat flux, net ground heat flux over the day, is 0, because the surface is not getting warmer, cooler, otherwise the Earth would explode if it was not the case. Therefore, we use option for daily data, we use soil heat method option 3, which simply says that soil heat flux is 0. This is the first very important caution when working with daily and monthly and yearly data. We use option 3. If we work with sub-daily data with less than 3 hours spacing between points, then we use 0 or 1 or 2. Let's see. Here in set options, by default, we have soil heat method option 2, which means that we are taking 35% of net radiation. All right, coming back to true meteorological data. The true meteorological data is stored, for example, in input, dataset mscope TS, EC, and Berkeley. Usually this file has many columns. What's important for us, this is, by the way, a FluxNet format. So you see, if you are familiar with eddy covariance technique, this is standard format of FluxNet data that we also adapted scope for. So what we have to say in file names file, we have to say that we need another folder, and the folder is called mscope_TS in my case, TS not capital. So the dataset space will be pasted automatically. And then we use the file name with extension. So Meteo EC CSV is EC Berkeley CSV. We can also rename this just for fun. And then all columns are now named differently. So what we have to do to be correct, we have to remove all column names and think which ones do we really want to use and which ones we don't want to use. T, we have to use always. We have to specify what timestamp it is. Timestamp has two values, timestamp start or timestamp end. you see the format is very interesting. It's year, month, date, hour, minute. The scope accepts this format also without those two. It's a standard format. So in file names, we say timestamp start. Then, remembering what I've just told you, let's see how frequent this data is. So this data is, you see these values are changing every 30 minutes, which means that we have to select 0, 1, or 2 as soil heat option. It is 2 by default. Okay, we just checked it. Then let's use basic input, radiation, temperature, humidity. That affects everything. Air temperature is this one, line 39. Radiation has two components, the incoming component the shortwave component and the incoming long wave component. So it's atmospheric radiation. And let's see what about humidity. We have here a VPD or even a gap field with MDS. VPD is vapor pressure deficit. So we can accept it, line 43. So actual humidity, relative humidity, and vapor pressure deficit are alternative options. We can use any one of them. And if we use relative humidity or VPD, a scope will compute EA. If we just use EA, it will use EA, actual humidity. All right, so radiation, temperature, humidity, time. All right, save it, go to scope, run it. The file has 3 days, 3.5 hours, so it will take some time to compute. But because we are using light option, it's quite fast, 11 seconds. Let's take a look at the output. This time series 1, I call this to differentiate a bit fluxes. What we can see, let's look here first in the input. In the input, we can see what we can say about these dates. There are 3 days with incoming radiation around 200 watts per square meter, so it's a clouded day, and then 2 quite clear sky days. Let's see what scope thinks about net radiation in those days, so the radiation that stayed on the ground. Okay, this is also quite low, around 180 at the peak, negative, yes, below 0 during night, as was explained by this figure. And yeah, roughly like that. That follows the pattern. Of course, latent heat flux follows the pattern, and sensible heat flux also gets negative during the night, as was explained here. Let's look at the ground heat flux. Ground heat flux actually is not getting negative here because we are using a 30% net radiation always. All right, let's compute one more thing that is important for further discussion. This is energy balance error. So the error is the net radiation minus sensible heat flux, latent heat flux minus sensible heat flux minus ground heat flux. So what we will see here, especially if I change the format to a number, that the values are everywhere within 1.5 watts per square meter. And this is okay. That means that scope did the job correctly because the job was to partition net radiation computed with radiative transfer path to 3 fluxes so that this equation matches. That's how scope works. We intelligently adjust temperatures to match, to satisfy this equation. What does this say to us that there were no warnings. So the warnings before were that the scope did not quite match radiation sometimes. In this case, there were no warnings, although we see sometimes there's a very, very, very little errors of slightly higher than 1 mass per square meter. But it's always worth checking. It's another caution. It's worth checking this by yourself and excluding values if you see that the closure is unsatisfactory. Let's say above 10 mass per square meter, definitely something went wrong. Here you can see how many attempts scope actually needed to close the energy balance, and you see during daytime is a bit more. During nighttime, the transition period, it can be even higher. But anyway, scope in this case did a good job. I remind you, if you want to save this file with plots, then you have to save it as Excel, and because otherwise it's a CSV file, plots will disappear. But I don't want to save it, so it's all right. All right, so this is how to provide input to scope in time series mode. You change the directory. In the directory, you put a file with meteorological data, and there you provide columns with this meteorological data. If you're wondering where can we get meteorological data if we do not have a Guidance Tower, now you can refer to this paper where what we did is we took ERA5 land data hourly, aggregated it to daily from Copernicus Climate Change Service, and a leaf area index, because vegetation is also important and plays a big role in these energy exchanges. We took them from Copernicus Land Monitoring Service. So if you want to be even more precise and use scope proficiently with radiative transfer plus energy balance paths, the retrieval we may discuss in the upcoming videos. For the time being, you can use those data sets. They are relatively easy to access and download. Now, let's talk about millions of cautions and millions of small things that can go wrong. First thing is viewing geometry. Viewing geometry is computed from latitude, longitude, time zone. First thing, let's check how it was for us here. If we open partial input short, you will be surprised, but you will see here TTS. TTS is a solar zenith angle, which is 85, at night it's more than 85 degrees, but scope narrows it to 85. And during daytime, the values change. So if I plot it, I will see the perfect harmonic curves, but I will also see that here the solar zenith angle is 74 degrees max, because the period we're talking about is December, but December where is specified in the input files as input data default. Here at the bottom of the file, we see latitude, longitude, this by default location in Netherlands, and the time zone 1, time zone of Netherlands. So scope computed this value of solar zenith angle, and it computes it always. Because I remind you here, we did not provide this information. That's why it is very important to either provide solar zenith angle or that latitude, longitude, and time zone are specified correctly for your location. So scope can compute solar zenith angle, and it will compute it with time series mode, but you have to be sure that you compute it for your location and not the Netherlands. Also, another caution, very important one. These are, maybe by mistake, parameters that we call latitude and longitude, but they have nothing to do with geographic coordinates. These are shape parameters of brightness, shape, moisture model, both soil reflectance that we are probably going to touch in the later videos. So don't change these values change the true geographic latitude and longitude that are specified here. The caution number 2, sometimes it's just a warning and automatic correction is applied. For example, here we just issue a warning that we compute actual humidity from air temperature and BPD. Sometimes BPD is in kilopascals, but we will do it in hectopascals. To check which units scope likes, you can go to documentation, structs. Usually you could search in docs. So we're talking about meteorological data. And in input structs meteor, if we go down, we see here the exact units that scope is using for parameters. So you see that actual humidity is in hectopascals, air pressure is in hectopascals, sometimes radiation is in watts per square meter and not megajoules or something else. So this you have to take into account, the units. Third caution, we already touched on it, closure errors. This is what I was computing and I said there was no problems. But sometimes there are enormous closure errors of 1 million watts per square meter. And this happens because those parameters were not adjusted simultaneously. So let's take a look. Again, it's in input data default. We have measurement height that has to be above the canopy. So it has to be above canopy height, which in turn has to be above displacement height, which in turn, together with Z0, the roughness length, the sum of those parameters have to be lower than canopy height. Only this combination works with aerodynamic scheme. The typical parameterization is to keep displacement height as 2/3 of the canopy and roughness length of 10% of the canopy. But if you see enormous closure errors and you're sure that your geometry is correct, the next thing to check is the height. And the final caution is the format of time. There are two aspects to be taught here, that we can take two time formats for legacy reasons with previous scope version. One is when we have year and Julian day of year, which can be decimal. So this can be fake. You can have it every millisecond and then have enormously large scope simulations. Or you can use this data format. But here the caution is, if you take a look at this Berkeley format that I used, if we see here, without saving, the Excel substituted this format by a scientific format. So this E in the power 11. That's why if I by mistake save this file now, I will break scope. You will see the error that we are going to receive is this one, that I'm unable to convert this timestamp because it's not anymore in this format. If I open it with some other program, you will see that Excel substituted our timestamp by this exponential notation. So if you're using very long timestamps, make sure that it's a string, or make sure that you do not save it in Excel, but rather use some programming environments, MATLAB, R, Python, whatever else. And the final caution, if you work with very large data, you can, if you want, to subset it with these parameters. So that says that we work from 2006 until 2030. So if you work earlier, you will realize that you have to change this date. This is, by the way, in the same format, year, month, date. You will have to change this value so that it covers full range. Or in contrast, if you want to subset, that it subsets your respective range. So this is very important. Sometimes you see your simulations are truncated, there are less numbers than you expect, then you may want to alter this. I believe I told you everything that is needed for you to run Scope in time series mode and to enjoy the weather-driven output. See you in the next videos.